is a great pleasure to be able to introduce Dr. Franklin A. Graybill on this occasion of videotaping a presentation by Frank for the archives of the American Statistical Association. This is the first of two tapes. The other consists of a discussion Frank held with several of his former PhD students here at Colorado State University. Before proceeding, I would like to thank Dr. Harry Poston, chairman of the ASA Committee for the Filming of Distinguished Statisticians, for his assistance in getting this taping accomplished. I've known Frank since the election day of November of 1964 when I interviewed here. Frank accepted a position here at Colorado State in 1960. He was hired to develop a graduate program in statistics, which he very successfully did. It included the hiring of many of our current faculty, including myself. I guess even someone with Frank's savvy is entitled to one mistake. We share common rural Iowa roots, so maybe he just felt sorry for me. Frank certainly deserves credit for the health of our department at this time. And ours is a department that this year celebrates its 20th anniversary, having been formally made into a department in 1971, with Frank, of course, as chairman. Further details regarding Frank's life and the department are part of the other tape. This is his tape, and he will make a brief presentation on variance components, a lifetime interest of his in our field of statistics. Frank?
Thanks, Dwayne. I want to thank the American Statistical Association for inviting me to give this lecture. I want to thank my students who I've had over the many years, and I want to thank Colorado State University and the department for giving me opportunity to work. And finally, I want to thank my family, especially my wife, Jean, for constant encouragement and understanding for over 44 years. As I understand it, I am to select a topic to discuss that I have been interested in for many years and explain the history of my involvement with this subject and with students who contributed to this area. Of course, I will not mention all students I have had, since many of them worked on other topics than the one I have chosen here. The topic is a fairly narrow one, but an important one, that of obtaining confidence bounds on linear combination and ratios of linear combinations of variance components. The science of statistics might roughly be called the science of means and variances, and a large percentage of the work is about means, with variances playing a subsidiary role as a quantity to evaluate means. Throughout the years, there have been scattered papers that treat variances in their own right, and with the emergence of the importance of the quality of products, components of variance are getting significant attention. I will discuss variances, and the specific problem I will discuss is that of obtaining confidence bounds for rho for small and moderate sample sizes, where rho is given by the sum of the AI theta I minus the sum of j times j of bj theta j over c naught plus the sum of ck theta k, where the ni si squared over theta I are independent chi-squared random variables with ni degrees of freedom. The ni and the si squared are observable, and the theta i's are unobservable parameters. No exact or even good approximate confidence bounds have been given for rho until recently, except for very special cases. For example, theta 1 minus theta 2, theta 1 over theta 2, or theta 1 plus theta 2. I will illustrate somewhat what the analysis of variance tables and what the models are where we might use this definition of rho. Here's an analysis of variance for balanced two-factor cross-random models without interaction. You can see that if you wanted to set a confidence interval on sigma squared A, it would be theta 1 minus theta p. If you want to set a confidence interval on sigma squared B, theta 2 minus theta p. If you want to set a confidence interval on sigma squared A plus sigma squared A plus B plus sigma squared E, it'd be some linear combination of the theta i's. Similar thing holds in a balanced two-factor cross model with interaction. Here, if you wanted to set a confidence interval on sigma squared A, it'd be theta 1 minus theta 3. Sigma squared A plus sigma squared B would be theta 1 minus theta 3 divided by jk plus theta 2 minus theta 4 divided by ik, and so forth. And in a three-factor crossed balanced designs, it'd be similar things here. To set confidence intervals on linear combinations of the variance components sigma squared A, sigma squared B, or sigma squared C would be setting confidence intervals on linear combinations of the theta i's. In 1951, the year before I graduated, an issue of biometrics was devoted to the topic of variance components. S. Lee Crump wrote the lead article entitled "The Present Status of Variance Components," and his reference contained 39 papers. There were probably a few more papers that could have been cited, but it showed that not much work had been done on variance components at that time. A bibliography by Sahi in 1979 contained well over 1,000 references. In supplementary bibliographies by Curry and Sahi in 1985, and by Sahi, Curry, and Kapadia in 1985, some additional papers were listed. However, less than 150 of the articles at that time concerned confidence bounds for functions of variance components, and all but about 25 or 30 concerned applications. Less than 10 papers related to new procedures for confidence bounds for rho for the general case. In the past 20 years, a significant number of publications have resulted that dealt with point estimators and variances of point estimators. Several names could be mentioned and should be mentioned, like Searle, Harville, Rao, and others. Crump's references contained only 3 papers that dealt with confidence bounds for variance components. His references also contained the classic 1947 paper by Churchill Eisenhardt entitled "The Assumptions Underlying the Analysis of Variance," in which he defined 2 models, a fixed effect model and a random effect model. These definitions are still used today. Eisenhardt's Model 1, which is referred to as a fixed effect model, has an observation that's structured like this, where the mu, alpha sub I, beta sub j, tau sub k, gamma sub I, j, k, and so forth, are fixed effects. The ei, j, k is the only random variable on the right-hand side of this equation. For example, alpha I might be row effect, beta j column effect, tau k treatment effect, and so forth. Eisenhardt's Model 2, or random effect, is a random effect model, which looks very much like this one, except the driving mechanism on the right-hand side are all random variables except the constant mu. Now, there are also mixed models where some of these might be fixed effects and some of these random effects. In the article by Crump, he omits reference to one of the most important papers, the one by H. Fairfield Smith entitled "The Problem of Comparing the Results of 2 Experiments with Unequal Errors," which appeared in 1936 in the Journal of the Council of Scientific and Industrial Research. His results were used by Frank Satterthwaite in 1941 in his well-known paper Synthesis of Variance, which appeared in Psychometrica, and a companion paper in 1946, which appeared in the biometrics bulletin entitled An Approximate Distribution of the Estimates of Variance Components. The results of these papers essentially gave an approximate distribution of S1 squared plus S2 squared and so forth over theta 1 plus theta 2 plus theta k. If this distribution were known exactly without any unknown parameters, then this could be a pivotal quantity for setting confidence bounds on theta 1 plus theta 2 and so forth. However, this Satterthwaite considered this as an approximate chi-square distribution with degrees of freedom that did not depend on the thetas, but since the distribution was approximate, the confidence bounds were also approximate. This simple result has proved useful over the years and is still used a great deal today. The procedure is known as the Satterthwaite procedure, but perhaps should more accurately be called the Smith-Satterthwaite procedure. When I started working on my PhD thesis in 1951, I was acquainted with this issue of biometrics, and I became interested in variance components. I wrote my thesis entitled Quadratic Estimates of Variance Components under Professor Kempthorne at Iowa State University. In it I showed that for general balanced nested designs, that is Model 2 designs, if one used the arithmetic of analysis of variance for Model 1 designs, the procedure resulted in minimum variance, quadratic, unbiased estimates of variance components and of linear combination of variance components. After graduating, I took a position as assistant professor at Oklahoma State University and was one half-time consultant with the agricultural experiment stations. Problems arose in my consulting with geneticists, plant breeders, animal breeders, and industrial engineers that led me to consider proportion of total variances as well as individual variance components in crossed and nested components of variance models. In 1950, Lehman and Chaffee published a paper on completeness and its relationship to minimum variance unbiased estimation. In 1951, Bill Wortham, my first PhD student who is now deceased, and I published a paper showing that for the two-way cross-balance design, a Model 2 design, the analysis of variance for Model 1 designs resulted in estimators of variance components that were uniformly minimum variance unbiased. In 1961, a student of mine, Robert Hultquist, and I published a paper generalizing this result as follows. Consider the general linear model, which we can write this way and written out in a little more detail this way. Where for Model 1, a fixed effect model, the beta 1 might be a vector of treatment effects, beta 2 a vector of column effects, beta 3 a vector of interaction effects, and so forth, and this is the random error. Now, if we look at this as a Model 2, random components model, then mu is still a fixed constant, but the beta I would be multivariate normally distributed with mean 0 and variance sigma I squared times the identity matrix, and the same thing with beta 2 up to beta n. Under that situation, the covariance of y can be written as the sum sigma I squared xi transpose plus sigma squared e times the identity, which we write as just the sum of the sigma I squareds times the ai. In the paper with Hultquist, we defined and gave conditions for the sigma I squared and linear combinations of the sigma I squared to be estimable. That is, for unbiased estimators to exist. We also gave conditions for there to exist uniformly minimum variance unbiased estimators of the sigma I squared and linear combinations of the sigma I squared. The conditions are very simple. They are that the AI and AJ commute for all I and j. We also defined complete balanced components of variance models and showed that the sum of squares in this case for Model 1 is a complete sufficient statistic for Model 2. It is interesting that R.A. Fisher in the 1920s defined and coined the phrase analysis of variance to analyze means in Model 1. This same analysis of variance leads to complete sufficient statistics and uniformly minimum variance unbiased estimators in balanced, complete Model 2 designs. When working with Professor George Godfrey in avian science at Oklahoma State University and Frank Martin, a master's student in statistics, we obtained approximate confidence bounds on sigma squared A over sigma squared A plus sigma squared B plus sigma squared C for the three-factor nested balanced designs. Professor Godfrey wanted this for studying heritability. To check the approximate confidence bounds on this, we used simulation. The computer, or we might call it a calculator, we had at that time did not have stored programming, and the random numbers that we used were on punch cards. We used the same 100,000 normal 0-1 deviates over and over and over. We would wire boards instead of writing programs. The procedure for setting confidence bounds on row sub A worked fairly well, we thought, even though to test it required hours on the calculator and was not very precise. We published a paper in Biometrics in 1956 entitled Confidence Intervals for Variance Ratios Specifying Genetic Heritability. In 1957, another master's student in statistics, Bill Robertson, and I used asymptotic theory to obtain similar confidence bounds. We published a paper entitled Calculating Confidence Intervals for Genetic Heritability in the Journal of Poultry Science. We thought this procedure worked fairly well for breeders in avian science and plant science, since they generally used a large sample sizes, a large number of chickens and a large number of plants. But the procedure did not work for breeders of larger animals, since typically they use small sample sizes. In 1960, I came to Colorado State University and did not work on variance components until the middle to late 1970s, when I again became interested in confidence bounds for variance ratios specifying genetic heritability. Between 1951 and the middle 1970s, several papers had been published on confidence bounds for variance components and positive linear combination of variance components. But almost no work was done on confidence bounds for general linear combination of variance components and ratios of variance components. Some people who published papers relating to these problems were Bartlett, Bross, Bulmer, Green, Healy, Howe, Wheatson, Morguti, Tukey, Wald, Welch, and Williams. It is interesting that most all of these papers concern mainly confidence bounds on theta 1 minus theta 2 or theta 1 plus theta 2. Only 3 papers considered confidence bounds on ratio of variance components. The history of this is approximately as follows. For setting confidence bounds on theta 1 plus theta 2 up to theta sub k, there are 3 general procedures. The Smith-Satterthwaite procedure that I referred to before, a procedure by Welch in 1957, which improved on the Smith-Satterthwaite procedure, and a procedure by Graybill and a student of mine, Wong. Now, the Smith-Satterthwaite procedure and the Welch procedure gives good lower bounds for all sample sizes greater than 5. Reasonably good upper bounds and two-sided bounds if sample sizes are approximately equal or if the minimum sample size is greater than 30. The Graybill-Wong procedure gives good upper bounds and two-sided bounds for all sample sizes, and later Wong gave exact confidence bounds for theta 1 plus theta 2 for lower and two-sided bounds. The reason I put exact in quotations is that his procedure was an iteration procedure which he could get the bounds to be as close to 1 minus alpha as desired. I want to show you a table on some of the results of this. These are results of 95% confidence bounds for theta 1 plus theta 2. They are the lower intervals and the upper intervals. The three procedures are the Satterthwaite procedure, Satterthwaite-Smith, the Welch procedure, and the Graybill-Wong procedure. Now, the reason that there's a range here of the confidence coefficient is that these procedures are all approximate and they depend on the unknown parameters. And as the unknown parameters vary over their domain of definition, the confidence coefficient will vary also, and these are the minimum and maximum value that the confidence coefficients vary. You can see that for small sample sizes, Welch procedures works quite well for lower intervals or upper bounds here. The Graybill-Wong sustains the 95% but goes higher. But as the sample sizes get further apart, this is a 95% confidence interval, the Satterthwaite procedure breaks down. The Welch procedure is not as good. And for sample size I don't have here, for something like 5 and 100, the Welch procedure even gets much worse. The Graybill-Wong procedure stands up pretty well, but the confidence coefficient can be higher than would be desired. Incidentally, the lower bound is the hardest, the upper bound is the hardest to find good confidence coefficient, but it's the one that you would probably want, because you would like to know if a variances is less than something, not if it's greater than something. Now, when you're talking about heritability rho, there you might want to know if it's greater than something. Now, for the lower bound or upper intervals, you can see the Satterthwaite procedure is pretty good for all sample sizes. The Welch is better and very good. The Graybill-Wong seems to have the upper bound, what you would want to be the lower bound. So it doesn't work very well there. Now, I give two-sided confidence intervals. We look at it, and we look at this for 90% confidence intervals for the same sample sizes. You can see the Satterthwaite procedure is not too good. The Welch procedure is not as good as might be. The Graybill-Wong procedure is very good. Another advantage of the Graybill-Wong procedure is that the width of the confidence interval can be substantially less than either the Welch or the Satterthwaite procedures, and particularly less than the Welch procedure. Continuing with the history of the period from late 1950s up to the middle and late 1970s, the procedure that was available, the good procedures, was the procedures that were available for setting confidence intervals on theta 1 minus theta 2 broke into three groups: Tukey-Williams procedure, Morigudi-Bulmer's procedure, and the Howe procedure. The Tukey-Williams procedure is quite good. The Morigudi procedure is better. The Howe procedure is best and very good. I won't show you tables for these, but it's interesting that even though variances, you would think the sum of variances might be easier to obtain confidence intervals on, that is not the case. The difference of variances is surprisingly easier to obtain good confidence bounds than the sum. The difficulty with all of these procedures is that they do not easily generalize to the sum of I equal 1 to P of Ci theta I minus the sum of J equal P plus 1 to Q of Cj theta Q. If you don't have just the sum of two thetas, the difference of two thetas, and then these procedures don't generalize well. And if you have a negative confidence, negative theta in here, the Welch and Satterthwaite procedure break down completely. And so they're not good at all. In a paper in 1990 by Ting, Burdick, Graybill, J. Ratnam, and Liu, we all got in the act there, we gave a procedure for setting a confidence interval on the sum of theta I minus the sum of theta J. I've eliminated the CI's in here just for making it a little easier to type and to read. We let L denote a lower confidence bound on delta for this problem, L less than delta. Then L, the way that we did this was L is equal to delta hat minus the square root of V sub L, where delta hat is given here is the unbiased estimator, is an unbiased estimator of delta, and V is a fourth degree polynomial, fourth degree homogeneous polynomial in the SI squared. You can see it all here now, but I don't think you're going to write it down and remember it anyway. This procedure worked quite well and worked as well on theta 1 minus theta 2, that simple problem, as the best procedure up to this point, namely the Howe procedure. Give you a table of how some of the procedures here, how good they were. This is a case where we had 6 thetas. In this case, for example, we had theta 1 plus theta 2 plus theta 3 plus theta 4 plus theta 5 minus theta 6 for these different sample sizes for the corresponding thetas. Here we had the sum of 4 thetas minus 2 thetas for the corresponding sample sizes here. Now, for the upper interval, the lower level, this procedure fell somewhat short. We'd like to have that be closer to 0.95. The upper bound, which is, and two side, which are more important, they perform quite well, although they get too high, which might make the confidence interval wider than we'd like. The two-sided interval, which is the most important of all, they performed fairly well. Now, we look down here at some of these cases, you see the sample sizes as small as 1 and 2, which is very, very small for variances. They still worked fairly well. This procedure worked fairly well, particularly the two-sided interval. And here's some more where you have 3 pluses and 3 minuses with sample sizes, for example, of 1, 2, 4, 8, 16, and 32. This is what you might have in a nested design, and the two-sided confidence interval works fairly well. Next, I will consider approximate confidence bounds on ratios of variances. For example, you might want a confidence bound on sigma squared E over the sum of sigma squared E plus sigma squared A plus sigma squared B plus sigma squared E for a threefold nested design. This is used in industrial engineering, certainly used in animal science, plant sciences, and a lot of other situations. Want to know what proportion of the total variance does, for example, sigma squared E contribute? By the end of 1970s, very little had been done on these type of problems. The procedure used on these type of problems was the Satterthwaite procedure. I referred to attempts that I had made in the 1950s with limited or little success. In 1978, Wong and I obtained reasonably good results for setting confidence interval on rho sub E and other ratios of confidence of variance components for the three-factor nested design. Arteaga, Jayratnam, and I obtained results for the two-factor cross designs without interaction, and Leive and I obtained results for the two-factor cross designs with interaction. In 1990, Ting Burdick from Arizona State University and I used the procedure for setting confidence bounds on linear combinations of variance components to obtain confidence bounds on ratios of variance components. We used an approach for ratios of linear combinations of variances similar to the one Feiler used for ratio of means. Remember, we got what we thought was a pretty good confidence bounds on linear combinations of variances, and we want to get confidence bounds on ratios of variances. A confidence bound on rho sub B, where rho sub B this, can be obtained by getting a confidence bound on the sum of AI theta I over the sum of Bj theta j, where the AI and Bj are positive constants. A confidence bound on rho sub B can be obtained by setting a confidence bound on the sum of the AI theta I over the sum of Bj theta j, where AI and Bj are positive constants. Consider the confidence bound L, where L is less than or equal to rho sub E. If we substitute for rho sub E, we get this. If we substitute this for rho sub E, we get L less than or equal to this. And after simplifying, we get this quantity here. And for fixed L, this is a linear combination of the thetas. So what we did was use the procedure I discussed before to set a linear combination, to set a confidence bound on this linear combination. Now that confidence bound, of course, will contain L. Then we set that confidence bound equal to 0 and solve for L, and use that then in the confidence bound for rho sub E. I will illustrate by simulation. We evaluate this procedure, and I'll illustrate with some tables. This is a case where we had the ratio of where P is 2 and Q is 3. That means we had 2 thetas in the numerator and 1 theta in the denominator. Degrees of freedom were 5 and 5 for the theta i's in the numerator and 5 in the denominator. The two-sided confidence intervals by Satterthwaite was quite good, and by Ting et al. It was quite good, but not as good as the Satterthwaite procedure, because this got higher than this. This was about the same. But then pretty soon the Satterthwaite procedure, for a certain sample size, Satterthwaite procedure breaks down completely. Look at where you have 2 and 5 in the numerator, 2 and 49 in the denominator. You have two thetas in the numerator, 3 in the denominator. Degrees of freedom in the numerator are 2 and 49. Degrees of freedom in the denominator are 4, 4, and 4. Satterthwaite for 90% gets down to 80, but the Ting et al. Procedure stands up pretty well. And down through here, you can see that the Ting procedure gives pretty good results. And where the Satterthwaite procedure sometimes gives very, very bad results for different sample sizes in the numerator and denominator. So we think that procedure is quite a good procedure, can be generalized to setting confidence intervals on general rho for balanced designs. The model I have been discussing so far are balanced, complete models. Some work has been done for unbalanced models. Curry and some of his workers have given a method that can be used for unbalanced, two-way crossed, and three-factor nested models. The drawback with their procedure is that it is not investigator invariant, and it essentially discards data. Srinivasan, Sen, Kazimpur, and I, 3 of my students and I, have developed methods by similar procedures discussed here, using unweighted means to set confidence bounds on variance components, linear combinations, and ratios of variance components. These methods give fairly good confidence bounds, even for quite small sample sizes, but I shall not go into them here. This is about where confidence intervals on variance components, linear combination, and ratios of variance components stand today.